Well, good morning, everyone. And indeed, we're starting up again with a series of webinars, and this one happens to be the first of that series. And I just wish to welcome everyone who is logged on to this webinar. And for those that are on the webinar that are unfamiliar with FRI's Mountain Pine Beetle program that was established in 2007, let me say just a few words to acquaint you with the research accomplished since the program was established. Its establishment was in direct response to an immense threat posed by the mountain pine beetle to Alberta's pine resources and Canada's eastern pine resources. The Mountain Pine Beetle Ecology program has operated with the support of an activity team that is comprised of government and forest industry representatives. And over the past 14 years, the program has supported over 40 research projects by leading scientists from universities, governments, and other research organizations. Projects undertaken fall under one of 4 research themes and respond directly to any one of 29 critical questions or priorities that were identified by the activity team. The research themes include beetle biology and management, hydrological impacts of mountain pine beetle, landscape and stand dynamics following mountain pine beetle, and social and economic implications of a changing landscape. And if you wish to have more information, I invite you to visit the FRI website or give me a call, send an email to me, and I'd be happy to respond to you right away. The project that you're going to hear about today falls under the first research theme of beetle biology and management. Early on in setting priorities, spread modeling was identified as a critical aspect of managing the expansion of mountain pine beetle. Over the years, a variety of models and platforms have been developed, and all have proven helpful in creating operational strategies and allocating resources. I will now turn to the main event of the webinar by introducing the speakers who will engage you on their topic, entitled Forecasting Eruptive Dynamics and Spread of Mountain Pine Beetle in East-Central Alberta. And the speakers are, and you have their picture on the screen in front of you. The first speaker is Dr. Barry Cooke, or the first individual I will introduce is Dr. Barry Cooke. Barry is a research scientist at the Canadian Forest Service, Great Lakes Forestry Centre in Sault Ste. Marie, Ontario. Barry has studied mountain pine beetle for well over 15 years and was a lead author in developing the 2017 National Response Strategy for slowing the eastern spread across Canada. The next participant in the webinar is Dr. Alex Chubaty. Alex is president of Forecast Research and Analytics, an ecological consulting company. And Barry, I must admit that Alex has also worked many years with Eliot and along with Barry, and has been a associate scientist at the Canadian Forest Service. He's an ecologist and simulation modeler, developing landscape models of insect dispersal and forest disturbances. Alex is a co-creator and developer of the Spatial platform that you will hear about today. And then we have Dr. Eliot McIntire. Eliot is a research scientist at the Canadian Forest Service in Victoria, British Columbia. He has been modeling flying insects for almost 20 years, including mountain pine beetle. He is the lead scientist of the Western Boreal Initiative and the Spatial Open Modeling Project. His focus is on building forecasting tools and nimble models. You'll have to explain that a little bit later on, Eliot. And has become a part of adaptive approaches to landscape management. So you can see we do have some leading scientists for this webinar, and without any further delay, I'll turn it directly over to Eliot. Okay, Eliot, please.
Thank you, Keith. Thank you for the introduction. I am just going to just start this presentation by going over the outline. with the outline are obviously objectives and then some fairly straightforward components. And each of the components I've labeled beside the name of the person who's going to lead that part of this talk. So Barry will begin with a lot of the background and sort of some of the foundation of where this project started and uses a lot of that work. And then Alex will go through developing what we did, and I will then present the results. And then we're all going to chime back in at the end to talk about next steps and implications. So the objectives for this project, and then what we hopefully will achieve in our presentations today, is to present a novel large-scale spatial dispersal model that bridges the well-known stand-level models that have been developed over many years. Second is to forecast the next decade of mountain pine beetle eruptive growth and dispersal at large scales. And I have the little thumbnails on the right. We're going to go deeper into each of those, but you'll see sort of that the map shows the study area. That's what we're talking about for large scales. 3, provide concrete quality assessments of model forecasts so that we can actually determine not just what the forecasts are, but how reliable they are. And finally, to provide the policy level support for national level mountain pine beetle risk assessment and containment strategy. And so with that, I will hand it over to Barry.
Thank you, Eliot, and welcome everybody to the seminar. Keith outlined at the start, we got interested in mountain pine beetle when it came over in large numbers from British Columbia, especially in the summer of 2006. And you had mountain pine beetle dispersing into even in 2006, it was dispersing into a very different kind of landscape from where it had originated, dispersing almost as far as Whitecourt in central Alberta and going through this more fragmented spruce, aspen, mixed wood matrix as compared to the pure lodgepole pine of British Columbia. And so we realized that we had an epidemiological forecasting problem where predicting spread in a new landscape, in a new environment, in a new climate was going to, you had a difficult challenge of making use of existing data from the Central Rocky Mountain region and trying to extrapolate from this to a very new landscape. That's a very challenging prediction problem. And it's akin to what you have in invasion ecology, insect invasion ecology, or even disease spread like with the novel coronavirus. You're trying to predict the behavior of a new agent in a new landscape. So you're dealing with a lot of uncertainties, and it creates a very interesting risk assessment forecasting challenge. By 2012, over in the next frame, mountain pine beetle had gone well past Whitecourt, was more than halfway across Alberta, as the GPS indicates. From this photo from Erica Samus-Lee, mountain pine beetle were found north of 60 in the summer of 2012. So the host range was expanding, the geographic range was expanding, and the problem of forecasting future spread based on limited sets of data from the home range back in British Columbia and the Central Rocky Mountains of the US, the problem was not going to go away. And this was creating a pressing policy context back in 09, 12, through those years, trying to figure out what risk really did the big outbreak in British Columbia represent for future eruptive growth and spread across Eastern Canada. That's the big picture context. And I do have mouse control. That's good. So this is really the end. The slide that I want to end on is this one. So I'm going to start with my ending slide and show you how we arrived at an aspatial stand level model of mountain pine beetle eruptive growth potential. You need to understand a little bit about how these growth models work to have some intuition and some confidence in the spatialization in the Landar MPB model. So this is where it all starts. Eruptive growth potential I am defining as the area between the recruitment curve, which is in this case is shown as a parabola, and R equals 0 replacement line where mountain pine beetle populations do not grow. So this shaded pink area is labeled EGP. That's the eruptive growth potential of a population. And the trick in invasion ecology is figuring out the shape of this curve, because the shape of this curve determines how much eruptive growth potential you have. The further left, the unstable equilibrium point, then the quicker an outbreak is to start, and the further right, the stable epidemic equilibrium point, the larger an outbreak grows to. And the higher this curve, the faster it goes from incipient stage at I to the epidemic stage at P. So this parabolic curve exists in theory, but the challenge is to put numbers on this in the home range back in British Columbia, and then to try to figure out what to do going forward with mountain pine beetle in an area where it hasn't been before. So the trick is getting actual numbers on the y-axis, which is the recruitment rate, and then the x-axis, which is the log. Here it's in log scale, log-based 10 attack density in trees per hectare per year. The way that mountain pine beetle operate as an insect, its reproductive strategy is to aggregate at low densities, get to enough numbers so that it gets to this incipient threshold. Once it is above this threshold, and in this case, this xi is located at about 0.5, so that's about 4 trees per hectare per year. So once populations get up to attacking 4 trees per hectare, then away they go to the outbreak level, and they will then be removing about 20 trees per year per hectare. So that's what an outbreak is. It's moving from this unstable open circle to this stable black circle. And eruptive growth potential is the area under that curve. The other point in this graph is that, of course, as climate becomes more suitable to pine beetle, reproduction improves at all population densities. And so that can be represented as a vertical shift of this parabola labeled RPX. That's the reproduction curve given an attack density of X, moving to this position at R prime PX. So an improvement in climatic suitability increases the eruptive growth potential. The other point that you have to understand about this parabola is it's the joint product of 2 independent effects. You know, when mountain pine beetle are at low density, then and this, of course, my image is inverted on the screen here, so this doesn't work so well. I'll just use the pointer. When mountain pine beetle are at low density, they need to aggregate in larger numbers, and then the eggs and the young larvae have an ability to overcome the host tree defenses. If they are attacking in too low numbers, these populations will simply drop down to extinction, and they have to get up over this threshold. So the positive phase of growth here is largely the effect of host tree defenses on eggs and young larval recruitment, whereas the declining phase is largely the effect of competition. As trees are removed from a stand, then large larvae tend to starve, and beetles will tend to emigrate from a thinning stand. So you have 2 different ecological processes. One, cooperation on the left side of the curve, and competition on the right-hand side of the curve. So to build these curves requires you have data on those 2 processes, their ability to cooperate at low density and the problems of competition at high density. So where do you get data for that kind of, for building these curves? I did cursor down, and it's maybe just slow with the lag there. Okay, I'll build the lag into my speech. So where do we get the data from? The competition curves are easy to build because you can observe an outbreak at high density and just watch it proceed through time. And as the stand gets thinner and the beetles compete with one another and die and starve, and the beetles leave the decaying stand, we have lots of historical studies from the 70s, 80s, 90s throughout the range of the Central Rockies. And what Chris McQuarrie, a postdoc of mine, did back in 2008, when we realized this spread problem was going to be a persisting problem, he went to the literature and got data sets for all of these locations where there's a black dot in all of these states and the Kootenay up in British Columbia. and assembled competition curves. And this is the paper that he put out showing 4 different recruitment curves for 4 different kinds of stand conditions. And the top row are natural stands. So these are uncontrolled outbreaks. And then the bottom row are stands where a lot of thinning had been done as a kind of a quote unquote beetle proofing exercise. And what Chris noticed is that the recruitment curves have different shapes. In the thin stands, the recruitment curves tend to follow the negative exponential shape with a flat period of buildup and then a sharp tailing down when stands are decaying and larvae are starving and beetles are leaving stands. And the same pattern observed in this other set of stands. And in the natural thick lodgepole pine stands where no thinning was done and no control, the outbreak would often terminate without complete disruption of those stands. So the curves were, although they were negatively inclined, they didn't have the same steep negative tail off at the end. So we take this bottom row of curves to be indicative of what you might expect in a landscape where you've got half to a quarter, just a fraction of the basal area in pine. We take this as a better representation of what we expect for the growth and decline dynamics of mountain pine beetle populations. So, i.e., this might be more representative of what you might expect in a jack pine landscape where maybe only 10% of the forest is pine instead of these top curves. But let's talk about the dynamics of these curves and and how they conjoin with other data to create a complete reproduction curve. Remember, this is a partial reproduction curve. Lag. Hopefully that. So this is the same curves that I just showed you. These are now colored. The red curves are for the natural stands and the blue curves are for the thin stands. And what I've shown here is cobwebbing, which is the path by which populations grow to their equilibrium point. So here's the outbreak equilibrium. And for an outbreak that starts at a very low level, so this would be about 1 tree per 100 hectares, the number, this curve defines the schedule by which populations grow to their equilibrium level. So with this particular curve here, in 8 years, a population is able to grow from about 1 attacked tree per 100 hectares to about, let's see, 2, log 2, 3, log 3, about 9 trees per hectare per year. So in 8 years, the population has grown to its equilibrium state. So you can see that the flatter this curve is, the less eruptive growth potential that there is. If I go down to these thin stands here with this low flat curve, it takes 16 years and each one of these steps is a year growth. It takes 16 years to grow from endemic all the way to this equilibrium point. And this is a population that is going to grow to a maximum growth rate of 2 to the power of 2, about 4 trees per hectare per year. So this population does not have a lot of eruptive growth potential. And if you raise this curve by improving the climatic suitability, for example, you'll have more eruptive growth potential. The point here is I'm trying to make the connection between the overall recruitment curve, its shape, and how that influences the time to reach outbreak. And the lower and flatter that is, the longer it takes to reach outbreak and the more manageable pest problem you have. The higher that curve, then the more challenging a problem it is. So what I'm going to do is take these competition curves. Now these curves are based on outbreak data, aerial observations of places where there are visible outbreaks detected by fixed-wing aircraft going overhead. This slide is not changing. This lag is pretty annoying, but It seems to be about a 10-second lag.
It's actually me that's finally doing it. So if you just say next slide, then I'll do it when you need it.
Oh, thank you, Eliot, for the clarity. So these negative exponential competition curves have been used in other literature too. So this is an example from a 2009 paper, Powell and Bench from the Sawtooth National Recreation Area. And what they did was they fit a family of these negative exponentials year by year to an erupting population of mountain pine beetle in Idaho. And what you can see is that the recruitment pattern varies from year to year, depending on whether the year is cold, like 93, 91, 95 in the odd year, or in the even years, or past 1996 after the climate of Idaho had warmed up a little bit. So below this horizontal replacement curve, there is no ability for populations to grow up to an outbreak threshold, because this line, the recruitment curve, does not intersect the horizontal replacement line. It does for all these other years. There's an outbreak threshold where these curves intersect. So the point, if I advance the slide, thanks to Eliot, if I take a warm year like 2004 or a cool year like 1997, but not a cold year, but a coolish year like 1997, there's a big difference in the eruptive growth potential. The equilibration time for in 1997, it would take 22 years for a population to grow from a size of about 100 hectares. This is now measured because this is aerial detection data, not population data. 100 hectare outbreak will grow to about 20,000 hectares in 22 years. So there's not a lot of eruptive growth potential in a year like 1997. The red curve is a warm year in 2004. So we take the same starting point of 100 hectares, and each year we're growing this by the amount dictated by the recruitment curve. Growth through time, growth through time, growth. It takes 7 years to grow to the outbreak threshold of 120,000 hectares. So there's a lot more eruptive growth potential in the top curve, in the red curve, than there is in the blue curve. Next slide. And so that shows you what you can get from operational observational data from fixed-wing aircraft or from helicopters. But it doesn't tell you what's happening in the low end in terms of the effect of beetles cooperating with one another, coordinating their mass attacks, and getting up over the defensive threshold that's set by the trees. There were no such data. There were hints at it in the literature, but it wasn't really until Celia Boone published this paper in 2011 that we really got a very good picture from actual field data, not lab data, from Alan Carroll and Celia Boone. They showed that when you get into logical pine stands well before an outbreak is happening, which is hard, you've got to scour the landscape and try to find very rare instances of mountain pine beetle, and then devote tens of thousands of dollars every year to monitoring those stands. What they showed, looking at 6 stands in southern British Columbia, is there's this very strong positive relationship between the starting beetle population, and this is measured in terms of attacked trees per year, and the proportion of those trees that are successfully colonized by those attacking beetles. And there's 2 patterns of recruitment that are revealed in that paper, although they didn't highlight them in that paper. That didn't come until 2017. When trees are well hydrated and well defended, they have high crown trigger pressure and the ability to push resin out that pushes beetles out. At this point in the curve, beetles are getting pushed out by resin-producing trees because there's not many beetles attacking. At this point, you only have maybe 1 or 2 trees per hectare that are being attacked and attempting colonization. But if the number of attackers rises and rises and rises and rises up to about 5, 6, 7, 8 trees per hectare, now you have a large enough population pressure on those trees that the probability of surviving pitch out goes from 0 to 100%. So this is the important. This is what determines the left-hand side of the parabola that defines eruptive growth potential, this defines that left-hand branch of the parabola. And moreover, the left-hand branch of the parabola flexes depending on whether the trees are well defended and unstressed, which is the blue curve, or if they've been stressed a little bit with some drought, which is the red curve. So if we go next slide, this then gives us everything we need to create a complete model of eruptive growth potential. Now, for modeling purposes, for the recruitment rate is expressed in a log scale on the y-axis. So the curves change shapes when you log transform them. But this thick red curve then is the cooperation curve, which rises as a function of rising attack density. And the black curve are the competition curves from all those other studies that I showed you from the Central Rockies mountain region. Now, if I raise the blue curve to the blue dotted line, so that the two curves are orthogonal, so I've got all of the young larval survival in the red curve, and I've got all of the large larval survival in the dotted blue curve. Then, because they're orthogonal, these two curves equations can be multiplied, and what you end up with through that multiplication is this dotted line, this purple parabola, and that is the curve that I started off showing you with. That is the growth schedule and defining the eruptive growth potential for the average mountain pine beetle in an average stand in the Central Rocky Mountains region, if the stand starts from a relatively low basal area to start with. So that purple parabola is the basis for the model that we're going to talk about next. Next slide. This is then the slide that I started with. This defines the eruptive growth potential. It's the growth schedule. It's the core growth module for the aspatial model. Now, this is what you might define growth in a stand or in a cell, in a point. But the question is, there's two questions then. First, what happens if, and for a given climate, what happens if climate varies in space? Well, then you need to be able to shift this curve around according to climatic suitability. And what happens if weather varies from year to year? You need to be able to bounce this curve up and down temporally, and you need to be able to modulate its position spatially. So that's the first thing, is if you're going to accommodate the known importance of climate, this curve can do that, but you've got to spatialize it. The next thing, of course, is having a curve defining the eruptive growth potential of mountain pine beetle doesn't do anything if there aren't beetles in the system. Beetles have to come from somewhere, and there are only two sources. Source A is our local populations residing in an endemic niche, which you have a lot of in British Columbia, but you have none of in the invasive context in jack pine in central Alberta. In the case of invasion, it's always option B. The beetles have to come from somewhere else. So to spatialize this eruptive growth schedule requires some sort of a spatialization framework that allows you to handle the immigration and emigration of beetles and reflect the spatial and temporal variations in climate and weather. And so this model is useless on its own, except as a conceptual model, even though we now have parameters on the y-axis, we have parameters on the x-axis. We've got to spatialize this. And this is what we had in about 2011, 12, 13. And then Eliot and Alex came along, and we started to spatialize this into the Landar MPP model. And that's the topic of this talk, is the function of the Landar MPP model.
Hey, thanks, Barry, for that background. So I'm going to continue here just describing the model, how we built it, and how we put together the spatial components. And just give you an idea or a sense of where we ran this model. This is the study area that we use, the area in green. So this is a fairly large area covering a good chunk of the province and also extending into Saskatchewan. Originally, when we started this project, we were kind of working in a much smaller area, but we realized that there were a lot of edge effects and some other issues with a smaller area. So we increased the size to better capture the data of the mountain pine beetle attacks in Alberta. So this is the area that we're working with. You can see the blue area there is Lesser Slave Lake. So we do get a very large portion of the province covered in this simulation study. Of course, no model is any good unless you've got good data coming into it. So we used a variety of different data sources to help to use as inputs into the model. We were able to get pine layers from Kathy Blaker at PFC in Victoria, which were the same ones that she had used for the 2019 MPB risk assessments. That's the most recent risk assessment that came out. So she provided us those layers, which included jack pine and lodgepole pine, and those have pretty good coverage of the managed forests in both of these provinces. So they're not complete; they don't have a complete picture of all of the forested areas, but they give us a pretty good representation of what's on the landscape. We also use the historic MPB attack data from the Alberta government. Thank you to Carolyn Whitehouse for providing those for us. So we had all of the aerial tree surveys with all the red attack provided to us for that. And then, of course, as Barry mentioned, both the Macquarie and Cooke study and the Boone et al. Study, we actually had used those recruitment curves in order to put those into the model. And then we were also able to generate climatic suitability layers from Biosim and Biosim-R. Now, data acquisition, cleanup, and processing can be very time intensive. That certainly was the case here. In order to sort of make this workflow as sort of smooth as possible, we sort of broke up each of these steps into modules. So there's separate components that can be run individually. And we also then, this allows us to update any of those data sets. So obviously, when we started this process, this model back in would have been sort of 2014-ish is when I started my postdoc with Eliot. You know, we only had data up until that point, but every year as we were working on this, we were able to quickly accommodate, you know, updates to data sets over the years. So what I'm going to do next here is just sort of walk you through each of those different components, each of those different modules, just give you a sense of how each of those individual pieces work, and then we can talk about how we put them together into a single whole. So for the climatic suitability components, as I mentioned, we're generating these SLR indices, or these climatic suitability indices using Biosim. So there are a few different indices that we can use. The Logan index, which is sort of an indication based on sort of the summer biology, is one metric that gets used or that has been used fairly frequently. More recently, with work coming out of, for example, Kathy Blaker's lab, and of course, Jacques Renier's work on insect overwinter mortality. And there's another index that we ended up using for the bulk of the study, and all of the results we'll be presenting. We're using this Renier index, which captures that winter mortality. And there's also another index, the Safranik index, which looks at stand recruitment, MPB recruitment, and that had been refined for Alberta beetle populations. And then there's also a composite index, which is just a geometric mean of each of those. So the model gives you the option of using all four, or any one of the four, I should say, of those climatic suitability indices. And each of them, you know, sort of predicts slightly different, you know, sort of spatial results there. And you can see sort of what some of those maps look like in the figure. Now, as Barry summarized, we have a lot of, you know, many years of research on the in situ dynamics within these pine stands. So, Barry and Alan Carroll had, really developed that and formalized that spatial model in their 2017 paper. And our task was to implement this in a reusable framework that we could then couple with the dispersal component. So we know that there are large-scale dispersal dynamics, but we also aren't in a position to be able to actually measure individual beetles. Just given the scale of the problem, there's no way that we can tag each of those and see what's going on in the landscape. So we really are relying on what those beetles end up doing, which is attacking the trees, and we can see those red tops when we survey the landscape from those aerial survey data. So we get a sort of combination of the in situ dynamics, so the growth dynamics of those populations, and then we can see the spatial effects of those dynamics as those red tops sort of appear to spread across the landscape. And so we're kind of doing what's called inverse modeling, where we know what the outcome is, we know what the outcome looks like, and we're trying to figure out or deduce the way that we actually achieve that outcome. And of course, that process of that inverse modeling process works best when we already have most of those components figured out, and we're really just trying to work on sort of a few individual pieces, which in this case was really that spatial spread component. So to model the vegetation, I mentioned previously we were using the lodgepole pine and jack pine maps from the 2019 risk assessment. Because we're just forecasting fairly short term into the future, between 1 and 10 years, these simulations don't require that we fully capture the forest depletion and regeneration dynamics. So as sort of a simplification of the model, because we're just looking a few years out, we don't explicitly incorporate those dynamics. So that's a simplification that we made. And when we're looking at actually modeling the spread, we base this spread based on the pine abundance, so the habitat quality, so what's actually there on the landscape. We also incorporated wind direction and magnitude maps, which we also obtained via biosim. And then to get the spatial components, we parameterized dispersal kernels, and we calibrated those using those red attack data that we got from the province. So that was the piece that we're trying to fit, and we used a pattern-oriented modeling approach to basically, simulate a whole bunch of different sort of dispersal outcomes, and then we tried to match up how well those match up with the actual data. So that's where we sort of get that sort of matching the patterns that we see on the landscape, and that's how we're trying to sort of infer the process that leads to those patterns.
Okay, so that's my cue now. So I will move to results. There's going to be two parts. The first is validation. How do we create the credibility that makes models useful? And the second part is the forecasts, where we actually make very specific, concrete, data-driven forecasts of the future. And of course, forecasts are like the weather. They have to be assessed for how good they are, and they're not, a crystal ball of the specific future, but they're going to be probabilistic. I want to talk about the main way we validated was something called the forecast horizon. So I'm going to go through what it is, why we do it, and how does it help. So what is this forecast horizon? Well, it's a way to evaluate how good we are at predicting the future. It tells us, for example, how good we are at predicting 1 year into the future, but also 2 years into the future, 3 years into the future. And in this case, we have 10 years of data, so we can look at how good are we at predicting up to 10 years into the future. Normally, we would expect, the 1 year into the future prediction would be the best, and the quality or the reliability of that prediction would decline. So 10 years out would be the least good. And so this is a way of doing validation that hopefully gives a lot of insight into how good the model performs under multiple different time scales. So why we do this? Well, we do this to get that sense of how far into the future we can rely on our forecasts. And the easiest way to to sort of think about this is we all know already intuitively a forecast horizon concept for weather. So we know that 3 hours into the future, it's much more reliable weather forecast than 12 hours or 1 day or 7 days or 14 days. And while they don't publish the forecast horizon itself, we all, just because we keep seeing the weather forecast over and over and over, we get an intuitive sense of that reliability as the, as that horizon gets further away from the present. So yeah, closer in time is usually more reliable. So how does this help? Well, planning occurs at many different time and spatial scales. So for example, and this is two of many examples, Alberta may be most interested in 1 year forecasts so they can set up annual control, and Saskatchewan on the other hand may be more interested in further than 1 year, beyond 1 year forecast to see the probabilities of spread. So if we can determine how reliable they are at each of those scales, then we can be, people can be making decisions based on that. So the graph is actually the result of our forecast. So on the x-axis is the forecasted years into the future. So the 2, is at the left-hand side, and 10 years into the future is the right-hand side. And basically what we see is that there is a lot of variation in the early years, and so we do have more opportunities to know about a 2 year into the future test. So we have 2011 data, we can forecast 2013. We have 2012 data, we can forecast 2014. And so that's what this graph is telling us, is given all those 2 year opportunities to predict, this is how they line up, and given all the 4 year opportunities, 5, 6, and up to 10 year opportunities to predict, this is what we get. And so what we see is that it's fairly difficult, or it's extremely variable to predict the next year, 1 or 2 years into the future. And this is going to be possibly due to things like winters fluctuate in their drivers, mortality, how much mortality they do. But what was really surprising and interesting to us is that as we went further into the future, the forecast actually didn't decline. What happened is we just had less and less variation about how good our prediction was. I mean, so the blue line is a sort of a fitted curve to the best fit, but really there's a lot of uncertainty. So the dotted red line could also fit within those the uncertainty bound. So it's basically saying that we're fairly consistent from 2 years into the future all the way up to 10 years, but noting that we couldn't predict very precisely with high confidence at 2 years into the future in some years. And then to read this graph on the y-axis, apologies, I should have said that earlier, I have these labels on the right where higher up is an excellent forecast, middle is a very good forecast, and modest is a not particularly good forecast, but much better than random, let's say. And so I'm not going to go too much into what the area under the curve actually is, but just the higher up it is, the better. This is a more traditional way of looking at this. So this is how we fit the data, and this is 1 year predictions, where the red is the predicted number. So predicting 1 year into the future each time. And we certainly do fairly good in many of the years, but there's obviously, it looks like to be, some few years where it's over predicted and then a few where it's under predicted. But, we're definitely following the correct trend for these. Obviously, this is a spatial model, and so we can do the same thing with maps, and we can generate lots and lots of maps, but I'm just going to show this one, which is the 2021 cumulative attacked trees, log attacked trees. And on the left side is what the observed data show, and on the right side is the predictions from this model. And so what the best case scenario would be that these two maps look exactly the same, and if you blur your eyes, there's a fairly very good concordance. But as you go specifically into certain areas, you certainly can find places that are not as good as others. But overall, we certainly seem to get a lot of the spatial forecasting fairly well. We can convert this into the annual displacements, and this was a table that was created in the risk assessment. So we just brought in the data from the risk assessment. I mean, I guess we took the table structure and we calculated all these numbers. And we have two directions. Northward are the top two rows, and eastward are the bottom two rows. And so going across the table is the year. So what we observed in 2011 was an annual displacement northward of minus 106 kilometers of the core of the distribution. And then in 2012, we observed a 35-kilometer northward expansion and then a retraction, and we can see across here what that dynamic is. The predictions from the model are the next row, and you can see that there's, many of the years are very close. And if we summarize them in 5-year windows, we actually do amazingly well in both 5-year periods. In the eastern direction, some years were not nearly enough, quite off, but other years were very good, surprisingly good, given the amount of variation that does occur. So these are huge fluctuations, and the model was able to capture some of these and many of these. And so on these 5-year net, we did fairly well in most of these, and this one the 5-year window from 2016 to 2012, and in eastern direction, we were definitely a bit off. If we put all this together, so those are validation. So this is now about the actual forecasts themselves, and this is, one of the critical outputs of this project is this map, and this is a forecasted probability of mass attack by 2030. And yellows to reds are places that have a non-zero probability of being attacked, and then the greens are places that don't have zero probability of being attacked. So this map, we have the equivalent of this map for every single year: 2022, 23, 24, 25, etc. But this is the cumulative probability. And we have a similar forecasted net displacement as what I showed before. So the eastward direction over these next 5 years and northward direction over the next 5 years would be 41 and 31 kilometers. And the subsequent 5 years is quite a bit larger. And going into the details of why those two different 5-year periods are different would be an interesting conversation to address. And of course, I'm not going to talk about this other table, but we have actual annual predictions for these displacements and confidence intervals around them. Alex.
Okay. And Barry, feel free to jump in here as well as we discuss the management implications. So this is a figure that we didn't produce, but I believe this one came from the Canadian Council of Forest Ministers' Slow the Spread document from a few years ago. And this basically shows, what those growth curves mean for managing these mountain pine beetle populations. So in sort of the three sort of sections here, you've got this green section, which is the that eruptive growth potential in colder climates. This sort of gold yellowy one, sort of intermediate there, and then under sort of really favorable climatic conditions, sort of in the orange red. That's obviously massive eruptive growth potential. And this gives us insight, as Barry was sort of alluding to at the beginning of the presentation, about how much effort we can reasonably put in and expect to mitigate some of these serious outcomes and some of the serious impacts of mass attack on our forests. So with cooler weather scenarios, with cooler climates, cooler years, we can definitely get a better handle on knocking back those populations. So for some given amount of effort that we're exerting, we have a much better chance of actually knocking down those populations back below that sort of eruptive threshold. Whereas as we begin seeing warmer and warmer years, it becomes harder and harder, and eventually it just becomes impossible to effectively knock these populations back. So if you're starting from, sort of once we've already got a huge eruption sort of in progress, trying to knock it back to this point here doesn't get you very far, because in subsequent years, it just continues to grow quite quickly. And so you begin losing the control there. And so where our model, comes into this is helping to identify some of these areas where we do have a better shot at trying to knock back some of these infestations a little bit earlier. Barry mentioned at the beginning of our discussion that trying to basically survey for low beetle density populations in these forested areas can be quite challenging. It's rather intensive. And so you want a much more focused approach into where you're going to be investing that sampling effort, and then subsequently where you're looking to invest in some management strategies. Did you want to add anything to that, Barry?
I think we have to wrap up, so we need to get through the next component. So, okay. Yeah. So I was going to take over this slide for now, and we all just need to make very brief points from here on. So basically, this forecast is the beginning of making a business case for engaging new stakeholders. The forecast, if the level of credibility is high enough, which we have shown it seems to be, can help direct resources. And then this third point here we're going to dive into for a minute is about this idea of ongoing multidisciplinary land management efforts, how this fits into that, and how this becomes part of a foundation for adaptive management. In terms of this specific project for FRI research, we have the completely open model and all of the data analytical tools that are modularized and reusable and are fully open and public. And then 2 manuscripts that we put together. One of them is to be submitted soon, and one of them has been submitted and we have minor revisions. So that one should be published briefly, which talks about the whole creation, what we were doing differently this time in terms of building this around a forecasting framework. The next steps, essentially, Alex, I'll let you talk this one. Sorry.
Sure. Yeah. So as Eliot mentioned, he mentioned that adaptive management framework. One of the sort of bigger picture goals that we have with projects like this is that we can begin to assemble different model components, not just looking at say insect disturbance, but begin to bring in other landscape vegetation, wildfire. Look at other wildlife, other species, begin to pull these pieces together, and we can begin engaging more with decision makers, with stakeholders, and get not only continuous feedback into the modeling approaches, but also be able to update our data and do management like scenarios, and management scenarios that are not just focused on single species or single problems, begin taking a more holistic view of these ecosystems. There are a few tweaks that we might want to make to the model, especially if we're going to be forecasting further into the future, because as I mentioned earlier on, because we were only simulating sort of these shorter intervals up to 10 years, we made the simplifying assumption that we don't need to worry about stand depletion and regeneration. So obviously, if we're going to be going beyond that time scale, we want to start to include some of those other dynamics. We also made some other simplifying assumptions, like We allowed all of the trees on the landscape to be attacked, all of the stands to be attacked, but of course, really only stands that are more than about 60 years old really are the most susceptible to pine beetle attack. And there's some other tweaks that we can make as we get new data, in particular, sort of fine-tuning some of those parameters around the jack pine eruptive dynamics. Because the model right now sort of treats jack pine and lodgepole pine very similarly, but there might be some additional piece of the biology of the ecological puzzle that we haven't fully captured that might be relevant for this model. And then, you know, sort of broadly speaking, taking a model like Lander MPB, the one that we've developed here, and actually incorporating it into some of our other work, the larger initiative, which is the Western Boreal initiative that Eliot and I are both a part of, to incorporate, you know, these insect disturbance dynamics with models of succession and wildfire. And that is just highlighted here on the next slide. Oh, sorry, and just before I get there, I just wanted to talk a little bit about what made all of this possible. And that's the Spades package, or the Spades platform that we implemented in the R programming language. That's available on CRAN. It's an open source project. It's an open source modeling framework that allows us to do these forecasting models, but it also allows us to do a lot of other things. Ensemble modeling, we can examine cumulative effects, uncertainty analysis, risk analysis, and of course decision support. So there's a lot of potential here with the software that we've developed. And all of these models are intentionally designed to be modular, and that allows reuse, and we can update things as we get new data. If we want to change the study area, anything like that, we can readily do those things. We can also then, of course, integrate it with these other components, like I mentioned, vegetation and fire simulation. And because this is all done in R, we get a continuous workflow, and that's allowed us to facilitate this perfect approach, which is the topic of that manuscript that we've got pending in Ecological Letters. So just coming back now to the Western Boreal initiative, I don't want to talk too much about it, but just to show you the types of models that we're able to incorporate into sort of this single study and this single workflow. So we've got not only the Mountain Pine Beetle, the Lander MPB component, but we're also modeling spruce budworm dynamics. We've got fire and vegetation. We've also got models of anthropogenic development. So we've got harvesting, roads, and other, creation of other disturbance features on the landscape. And we're looking to see how these impacts, impact caribou, birds, carbon, and other factors and other species, and then ultimately linking all of these together into, being able to simulate and being able to examine different management actions and the impacts on these systems.
So I'm gonna be very brief here. One of the realities is that we work in lands and we study lands that are affected by multiple processes at the same time. So whenever we divide out the landscape into different topics, so for example, in this one is Mountain Pine Beetle, we might recommend, or it might impact management actions, but we sometimes forget that all of these things are actually connected in the landscape. And so, if we do something with Mountain Pine Beetle and Mountain Pine Beetle management, it's going to affect caribou through what the beetle does to vegetation and what Mountain Pine Beetle management will do to vegetation. But it also will affect fire, and through the various things, and of course climate change will affect all of these things. So what we've tried to create here, this model, is part of an interoperable system that we can build it into a whole where the scientific components are all connected to each other. And so the objective for doing this would therefore be to try to minimize the number of times that we're reacting in emergencies to a Mountain Pine Beetle situation or a fire situation, and instead we start to do a better job at doing land management that anticipates some of these things and doesn't, maybe we'll be able to minimize some of the impacts on things like species at risk, like caribou, while taking into account all of the various components. So with making this open interoperable framing of what we've done allows this to happen, and that's what we're doing with that Western Boreal initiative. Whoops. Alex.
Thanks. And I just wanted to sort of come back to this notion of the fact that we're working in R and we've established sort of a single continuous workflow. It allows us to very tightly couple the data import and analysis and cleanup and all of those things associated with bringing data into these models and directly linking them to the actual models, the simulations and the forecasts that we're doing. And because of R's rich package ecosystem, we're able to take these, take the data, take the models, and we can also begin to develop reporting and other tools that will facilitate decision makers as well as the general public to better understand the outcomes and the outputs of some of these complex models. So there are a lot of tools like R Markdown and Shiny in particular, which allows you to build very rich web applications, which have been really nice tools in trying to basically show results and to basically help communicate a lot of these results from these different models. So we're really excited about a lot of the possibilities that come out of this. Now that we're in this sort of a system, it's a lot easier to build on all of these other pieces.
Alex, do you want to put the slide, or Eliot, put the slide back to the your forecast of the 2030 scenario? You guys have reflected broadly, and so I want to reflect focally and narrowly. Back in Grand Prairie in the summer of 2006, I remember attending a conference, and it was the week that Alberta had declared an emergency of Mountain Pine Beetle, and a forecast put on the table by a group that was doing some CELIS-based spatial forecasting, and they made the prediction that Mountain Pine Beetle wouldn't get the Grand Cache, and you all know where that is on this map, until 2020. And it was the summer of 2006 in June, and I think they got there in July 2006. And I remember seeing the forecast thinking, that does not respect the eruptive growth potential that you have in British Columbia and Prince George and the northwest of British Columbia, and it doesn't respect the dispersal kernel of Mountain Pine Beetle, which is surely different in Alberta than in British Columbia, where you've got cloistered mountain valleys. I knew in 2006 we would need a different forecasting approach if we were going to have any credibility. And basically what Alex and Eliot have shown you today is with Mountain Pine Beetle predicted to continue to spread in small jumps to the Saskatchewan border by 2030, this is a much more credible, much more robust framework for making spread prediction than what we had back in 2004, 2006, which, it is what it is. It's an improvement. But what's interesting to me is that we're using the same source data in terms of recruitment curves based from BC. Those data were available. They were sitting there in 2004. They could have been used. That the framework could have been mounted in 2004, but we didn't have Eliot, we didn't have Spades, we didn't have Alex, we didn't have any of this. So the point is, we're using the same data that were available back then, making much better predictions now. And now we have a platform to actually do more if we want to, or stakeholders want to.